All right, so chapter 5 teaches us our first kind of chemical reaction that we kind of give a name to and that we'll start to use to help us understand chemical reactions a little better. We got a lot of fundamentals, but we're really just at the beginning, and we're going to start with chemical reactions in aqueous solutions. Now, I don't know if you remember, but we have kind of in the past talked about chemical, for example, let's say that I have some chemical XYZ, and I put a little S here. Remember what that S means?
Solid.
Solid, right. And I could put an L. Remember what the L means?
Liquid.
Liquid. And then G.
Gas.
Gas. And then what in the world is AQ? Do you remember that?
Well, that's aqueous, but I don't know what that means.
That means dissolved in water. Dissolved in water. So if I had my pile of XYZ here, and I put it into a container full of water, then now the XYZ here, which is XYZ solid, now I would say after it's in here, it's XYZ aqueous, dissolved in water. Okay? And that becomes kind of its own little thing. I mean, you know, we have solid, liquid, and gas, which are the three phases. Nobody ever talks about the phase aqueous because it's not a phase, but it's very critical in chemistry because for chemistry to occur, if I have some chemical reaction, any old chemical reaction, A plus B, and I want to make some C, right? I have some chemical reaction. A and B have to actually find each other. They have to find each other, collide, and then if they're going to move electrons or rearrange, that has to occur. That can't occur if they don't find each other. And you know, that's a general principle in our existence, right? There needs to be a contact made oftentimes for something to occur. So this contact is difficult to occur if, for example, my A and B or my reactants are both solid, right? So here, let's say I have a pile of A and a pile of B, okay? And I'm going to pour them together into some beaker where I want to perform the reaction. That's the plan. But, you know, we look at A and say, yeah, it's there and it's available and I can touch the atoms. But, you know, when you touch a grain of any material, it's much, much, much bigger than an atom, right? And all the atoms or molecules or whatever kind of material it is, compound, on the inside of that grain is not going to be able to come in contact with the B, right? So if I react two solids together, there's not going to be a really good chance that the reaction occurs. If I pour a solid and a liquid together, there's a chance, but that's not necessarily a guarantee that a reaction is going to occur. I mean, there's still going to be limitations in the ability for the chemicals to interact with each other. Two liquids will interact very well together as long as they're the same kind of property. If one is hydrophobic, like oil, and the other is water, then there will be a separation and there will only be a plane, a line where the two layers are laying on top of each other, where the reaction would be able to occur, right? So one of the best ways you could say that nature has kind of found for chemistry to occur is where A is aqueous and B is aqueous, right? Because in that case, I put A and B into water. So this time I'm going to put A and B in their own separate containers of water, okay? H2O there. And another one, H2O, right? Then, and this is A and H2O, B and H2O. If A and B dissolve in the water, then they spread out, and every single unit of that material is separate from each other and has space to interact with whatever it's going to interact with. Then when I combine them together into some reaction here, the A and the B, if they're both dissolved in the water and then they mix, they can interact very, very easily, right? And so the chemistry can occur, okay? So, and this principle is critical for any biochemical reaction that exists. That's why entities that, initially began chemistry were in the ocean, right? That's also why larger living organisms, or even smaller, right, all based on cellular life, the cellular material is essentially a high percentage, 60, 70, 80% water, right? Lots of water in there. I mean, for a cell, actually, probably more like 90%. But so aqueous chemistry is a big deal, and it's a fine place to start understanding our chemical reactions. Now, we need some vocabulary. We need some vocabulary to talk about things, okay? And these are the initial words that we're going to introduce. A solution is what we get when we have basically a mixture, right? So if I take A and I put it into my water, let me, fresh place to draw a picture. If I have my material, there it is, and I have my water that I'm going to dissolve it in, all right? Once I put the sample in the water and it dissolves, then I have my solution. Now, we're used to the word solution a little bit. Some people might be more used to it in terms of being like the answer to a problem or something. So don't get confused. This solution is, we have solubilized, which is another word we'll introduce, our chemical. In this case, we're talking about chemical A here. And so when it's aqueous, it's in solution. The solvent in a solution is what is in the highest concentration. And for aqueous solutions, that's almost always our water. You don't have to have an aqueous solution. There are lots of different ways that you can have solutions. Air is often referred to as a solution. And air contains oxygen, nitrogen, right? Those are the two main components. A little bit of carbon dioxide, I mean, a really little bit. Argon is also very little bit. But here, you'd say, oh, there's no water, so what's the solvent? Well, when there's no necessarily any water, or anytime we're mixing two components together, the solvent is what we call the chemical that's in the highest concentration. Solvent, all right? And then the other things all become identified as solute. Like A here is our solute that is going into our solvent, being water, okay? So solvent is generally going to be water, but there might be different scenarios where you have different chemicals as the solvent. Solute is the thing that's in the mixture, in the solution, that's in lower concentration. So that's usually going to be like an ionic compound or a molecular compound of some sort. All right, that's dissolving in water. All right, and then concentration expresses the relationship between the solute and the solvent, right? We're just trying to find out, how concentrated something is. That means how much of our solute is in solution. Okay. Few more vocabulary terms. Dilute. That means there's not very much what?
There's not very much solvent.
Solute. This is the solute,
Solute.
right?
Okay.
Because it's the thing
Right.
that's dissolving into the water. Does that make sense?
Right.
Yeah. So here I have some green and white solute, and down here on the bottom I have my water molecules. If I just put a little bit of solute in there, then I can say I have a dilute solution, right? And I think most of us will be familiar with what dilute means, right? Just a little bit of my solute in the solvent or in the solution. Concentrated solution can occur when I keep adding solute more and more. And, in the olden days, we used to have to put sugar in our cereal, right? Because it tasted like cardboard and you needed to have something in there to make it taste good. And well, we'd put sugar in and then we'd start eating, and then at the end, what'd you have at the bottom of the cereal? Sugar, right. A big pile of it on the bottom. And that was because there was more solute than that cold milk, which was the solvent, could dissolve, right? And so once that happens, if I keep adding solute until I reach a point that the solvent can no longer dissolve any more of it, then I have a concentrated solution. Concentrated, right? So if I have a concentrated solution, generally that's an indication that we're going to have extra material piled up on the bottom somewhere, right? It's concentrated. Now you might be right at the point where it's concentrated, but you've removed all the excess material from the bottom. That could be also a scenario. All right, so another word for kind of another way of thinking about concentrated, we can say it's saturated. Saturated. That's basically saying that all of the solvent, which is doing something to dissolve the solute, all of the solvent is occupied. It can't dissolve anymore. It's saturated with solute. Okay? And solubility refers to how much solute can be dissolved. So some solutes, some materials are not soluble. So like, for example, if I have some sugar on the bottom of my cereal bowl and I try to rinse it off, the sugar will dissolve away generally. But there's some things like if I have a little rust on the bottom of my cereal bowl for whatever reason, the water just won't wash it away, right? Because the rust isn't soluble in the water. I'd have to scrape it away to get rid of it, right? So not all chemicals, not all compounds are soluble in water. And some chemicals are more soluble than others. So their solubility thresholds different, right? How soluble the chemicals are can differ from chemical to chemical. If I have an unsaturated solution, that's a solution where it can have more solute. I can add more solute and more of it is expected to be able to dissolve. Supersaturated. Supersaturated means that we have more solute than we theoretically should be able to have. And that happens sometimes because we can change the solubility of a compound by raising or lowering the temperature of a solution. So, for example, a recipe for syrup, for pancake syrup, right, takes 2 cups of sugar for every cup of water. And, you know, that recipe doesn't dissolve all of the sugar. If you your mixture, and once you do that, then everything kind of gets into the aqueous or liquid phase, right? Aqueous, everything's dissolved then. But if you cool it down slowly, then you get a thick syrup as opposed to the salt or the sugar coming out and becoming a solid again. However, if you don't make it right, if you evaporate too much water off, then when the syrup cools down, big chunks of sugar will come out, right? I don't know if you've had that experience, but so what you've done there is you've attempted to supersaturate the solution, but then as it cooled, it decided to, we say, precipitate or form a solid, come out of solution like that. So supersaturation is more of a side note than anything right at this point. Now, if I have a compound, an ionic compound, then it becomes important for me to be able to know whether or not that ionic compound will be soluble in water or not, okay? And so we have what's called solubility rules, which allow us to think about any compound. So here's an example of a compound. And notice that this says solubility rules for ionic compounds in water. Solubility rules for ionic compounds in water. So this these solubility rules here are for compounds. And if I have an ionic compound here, sodium chloride, okay, I can use the solubility rules to help me find out whether or not a compound is going to dissolve when it's placed in water. Okay? So, let's see. The way we want to be able to do this, if I say, hey, can sodium chloride dissolve in water? What we want to be able to do is we want to be able to look through these rules and see if there's any rule about sodium or about chloride, right? Because those are the two ions that are in this compound. So, let's see. On the back of your periodic table, we have this table of solubility rules. And let's see if we can read through it and see we have any reasons to know whether or not sodium chloride is soluble. All right. So the first rule says right there, all compounds of the alkali metals, that's group 1A, right? All those are soluble. Okay, so that rule right there I think is going to help us, isn't it? Because sodium is group 1A.
Yeah.
So that means anything that has lithium, sodium, potassium, rubidium, cesium, francium, all of those are going to be soluble. All right. So we know that sodium chloride is soluble because that rule told us so. Okay? Let's look at another rule, or another compound. If you can tell me the name of this compound. Can you tell me the name of that compound?
Magnesium.
Yeah, that's right. Magnesium chloride. Very good.
Chloride?
So, let's see. Can we find any rules about magnesium ions or chloride ions that might tell us whether or not this is soluble? Look into your solubility rule chart. Can you read that okay, or is it too small?
Yeah. So So the ClO2.
Okay, so this is just Cl though, right? What about rule 3?
All chlorides. That's right.
Okay, so read through that rule because
all
some
chlorides.
of the rules, many of the
That's
rules
right.
have a little except at the end. So we have to make sure we read through it.
I see. Oh, I see. Chlorides, bromides, and
Iodides.
okay. So all chlorides, bromides, and iodine. Okay, salts containing CO, bromine, and iodine
That's
are
silver,
soluble except when combined with
silver, lead,
I don't know what
and or I should
Okay.
say or mercury.
Okay.
Mercury, that's a different kind of
And then
mercury
what's
ion.
subscript
That's-
2?
Yeah, there's two different ways that mercury ion exists, and that's one
Oh,
of
is
them.
that okay? Okay.
We don't talk a whole lot about that. It's kind of more on the fringe of it. Okay, but looking here at this compound, is that one of the exceptions? Magnesium chloride? Do you see anything about it? The only exceptions are silver, lead, and mercury.
Thank you.
So it doesn't apply. I mean, it's not
Right.
an exception.
Right.
Yeah, it's not an
So
exception. So
it
what does that
doesn't
mean?
apply.
Is
Yeah, I mean,
magnesium
it's
chloride
not an
soluble or
exception.
insoluble?
Soluble.
It's soluble. That's right. It's going to dissolve in water.
It's soluble.
Okay, excellent job. Here's some more. What's the name of that compound? Any ideas? The first one, the top one there?
Calcium chloride.
CO3.
Calcium
Oh, calcium.
chloride.
Not ClO3,
Oh,
just CO3.
calcium chlorate.
Oh, okay.
Oh,
Calcium chloride.
Cl.
Calcium carbonate. Calcium
Oh,
carbonate.
okay. Calcium chloride. Oh, carbonate.
Okay.
Where am I?
Good. Now, let's look at our rules.
Okay,
Look at the
carbonate.
rules and see if we can learn whether or not this compound is soluble or insoluble. So let's look at these rules. Which one tells us something about calcium carbonate?
Number 6.
Number 6, all salts that contain, yep, and there's carbonate, are insoluble. Oh, but there's some exceptions. That's either group 1A, so calcium is not in 1A, it's in 2A over here. Or the other exception is the ammonium ion. Ammonium ion. Okay, good. So that would tell us that the calcium carbonate is what? Soluble or insoluble?
Insoluble.
Insoluble. Very good. Insoluble. All right. Iron. Let's see if you can tell me what the name of that compound is. Here's a hint. It has to have a number with it. Iron something chloride.
Yes, every 3. So iron 3.
That's right. Iron 3. And the 3 is telling us that the iron has a +3 charge. Very good. Iron 3 chloride. So let's go back to our solubility rules. Anything about iron or chloride that we can think of?
Yeah, I thought I saw, let's see.
We knew rule 3 talked about chlorides before.
Oh, yeah. So what's up combined with, okay. So that doesn't apply.
Other than that, I don't see anything else on here about
So-
iron.
Yeah.
So it's
So
soluble.
it's
That's
soluble.
right. Soluble. Very good. Okay. This is lead 2 chloride. Lead 2 chloride. Let's go lead 2 chloride.
Okay.
Yeah, there's something there.
Yeah, there's something there.
So number 4, right?
So
Number 4?
number 4, right?
Uh-huh.
Or, isn't that right?
Well, it says
or,
all sulfates,
isn't
but all
that right?
chlorides. This
Well,
is a chloride,
3, too.
isn't it?
Yeah.
So all chlorides are
Yeah,
soluble
3, yeah.
except when combined with silver, lead, and mercury. Right? So that tells us that what? Lead
Yeah.
chloride soluble or insoluble?
Insoluble.
Insoluble. That's right. Won't dissolve
Insoluble.
in water. Okay, very good. So we have a method now, which is our solubility rules, ways to identify whether the compounds are soluble or insoluble. Now, sometimes people say memorize the solubility rules, and that's nice, but I wouldn't do that if I were you. What I would do is I would always use the solubility rules, and then once you use it enough, the things that you reuse over and over will always be in your mind, and you'll get enough of a remembrance to succeed on any questions that come your way. All right. And also in the long run, 10, 20 years from now, if you're not a chemist especially, recognizing the existence of the solubility rules is going to be more valuable than memorizing them right now. Okay, now here's a question about solubility of a compound. So we have sodium chloride here, and we're told that its solubility, meaning how much can dissolve in water, is 39 grams for every 100 grams of water at 100 degrees Celsius. Now, we haven't talked much about it, but we know that solubility is related to the temperature, right? We know that if you heat up water, more sugar dissolves in it, and that's also true of salt, right? If 10 grams are dissolved in 50 grams of water at 100 degrees Celsius, is the solution saturated, unsaturated, or supersaturated? And we're told that 39 grams can dissolve in 100, and now somebody tells us I have 10 grams in 50. Is that a saturated condition, an unsaturated condition, or a supersaturated condition? And I don't know, can you tell by looking at that what the answer is?
Well, it would be. So I'm, in my mind, I'm just.
Sure, that's good.
dividing it by half, right? And so I'm getting 20 grams
Yeah, that's right.
roughly.
And since fall short,
10 is, fall
Well,
short, I'm
what
going
about
to say none of
unsaturated?
these.
okay, so it's still dissolved.
Oh, okay. So it's
well, yeah,
so it's still
that's right.
dissolved.
The 10 grams dissolves in the 50
just-
grams.
It's just
but it's
unsaturated.
yeah, it's not
but
saturated.
It's unsaturated.
It's not supersaturated. It's
Okay.
it's just what we say unsaturated, meaning more can dissolve, like you recognize.
Saturated.
More can dissolve, so we're not saturated or supersaturated.
Oh, I see. It already says right there.
Oh, I
it's
see.
dissolved.
It already
Yes,
says right there it's
yes.
dissolved.
Good
Yeah,
point.
it's not very
Yeah. Okay. I'm just not
Okay,
reading that
good.
very well. Okay.
So let's talk about what happens when these ionic compounds, the ones that we're trying to decide are soluble or insoluble in water, let's talk about what happens when they dissolve in water. Okay? And we've seen this video a couple times maybe, but one of my favorites, so I watch it all the time. If we have a three-dimensional lattice of an ionic compound, in this case it's sodium chloride, but ionic compounds themselves in three-dimensional lattices of their respective ions. So here, sodium chloride, we have sodium ions and chloride ions. Okay? Again, this is what we call a three-dimensional lattice. And it's very, very important that we remember that ionic compounds reside in three-dimensional lattices. That's the first important thing to remember from this video. The second important thing to remember from this video is that when salt goes into water and what we call dissolves, what these salts, now I'm going to push pause again and remind you that when I use the word salt, that refers to any ionic compound. And in this case, we have a soluble salt. When a soluble salt goes into water, what's happening is the water molecules are surrounding the charged ions. And that ion is lured away from the three-dimensional lattice. Now, they're all lined up like that because they're kind of sharing electron density. The charges are being attracted to each other. But the water molecules entertain that charge and coax it away from the three-dimensional lattice. So we use the word dissolve because, that's what the world told us. And that's a fine word. But for ionic compounds, a little more than dissolving is occurring, and it's called dissociation. It's dissociating, or in other words, those ions are actually separating from each other and being entertained, surrounded by water molecules. So if I have down here, I'm going to write NaCl, and I'm going to draw these NaCl, I'll say solid, and I'm just going to put water up here to remind us that we are actually going to dissolve this water, or this ionic compound. Then what's happening is the sodium ion is being separated from the salt, and I'm going to show that it's aqueous. All right. Now, there's no other way that that sodium ion can exist in solution of any kind without something surrounding it and seeing that positive charge. And that's what that aqueous is reminding me. If I don't have the aqueous, we just have to know that if an ion is by itself like that, it has to be surrounded by water molecules. Then the other ions, chloride ion, is also surrounded by water molecules. So when somebody writes from now on or anytime an ionic compound and they write aqueous, then we have to remember in our minds, oh, that's an ionic compound, aqueous. That essentially is saying that we have, sodium ions and chloride ions. Okay? We have to remember that ionic compounds, when they go aqueous, they separate. And this separation is called dissociation. Okay? So, ionic compounds dissolve in water. That's still safe to say. But ionic compounds also dissociate in water. Now, sugar, C6H12O6, or glucose, we'll say, because that's an easy sugar to talk about. C6H12O6, sugar, or glucose, dissolves in water. It dissolves in water. But no metals here. This is not an ionic compound. So when I draw this aqueous, it just means the water molecules are surrounding that molecule and entertaining it. There's no ionization or dissociation that occurs. So when molecules dissolve, they don't dissociate. But when ionic compounds dissolve, dissociation occurs. Just like this video is showing, right? This is a compound dissolving, and upon dissolution, that means dissolving of the ionic compound, you get dissociation. Or some people just refer to it as ionization, because you're taking the solid and into its individual ions. Okay? All right. So, molecular compounds, same type of thing, but no ions result from the dissolving of molecular compounds. And because of that, because no ions result, you don't get any conductivity in a solution of water and sugar. It doesn't make the solution conductive. Here I have some water and a salt called copper sulfate. All right. Copper sulfate is soluble in water. It dissolves. And therefore, when I have this dissolved, AQ, essentially what I'm saying is I have copper ions and sulfate ions dissolved in solution. And those two ions, in this case here, are providing conductivity to that solution. Now we're going to introduce another word for conductivity, or for these ions in solution, and it's electrolyte. Electrolytes. Electrolytes is just a fancy word for a chemical that, when placed in water, it dissociates. It dissociates. Okay? Are you okay with the term dissociate? Does that term sit well with you?
Yeah.
Okay, good. Now, we have seen from the solubility table that some compounds don't dissociate and dissolve in water, right? Lead chloride, we said, does not dissociate in water, doesn't dissolve in water, so therefore it can't dissociate. And we can call that kind of a compound a non-electrolyte. It doesn't create electrolytes or ions when placed into water. Therefore, it can be called a non-electrolyte. Something like sodium chloride, we said that does dissolve. Solubility rules told us it dissolves. It's soluble. Therefore, it also, because it's an ionic compound, will dissociate. Therefore, it's going to be called a strong electrolyte. And different compounds vary in how much they'll actually dissociate. Some will completely dissociate. Every single ionic compound there will dissociate, whereas others will 90, 95, 80% dissociate, right? So there's different strengths, we call it, of electrolytes. A non-electrolyte doesn't dissociate. A strong electrolyte completely dissociates, whereas a weak electrolyte, it dissociates, but to a limited degree. All right? So the term electrolyte made, companies a lot of money that were trying to sell sugar water, basically, with salt in it. But it's nothing more than just ions dissociated in water. Okay. Now, we talked about how if I found Na2SO4, for example, I want to see if you can take a crack at naming that compound, Na2SO4?
Sodium sulfide.
Sulfate, sodium sulfate. Good, good. So if I have sodium sulfate here, and I put it into water
sulfide?
and it dissolves, I need to be able to, again, recognize that those two sodium ions, so I can't ignore that little 2 there, I need to make sure I see it. Those 2 sodium ions are going to dissociate away from the sulfate ions, and I'm going to have them floating around. Each one is going to be individual. Each sodium ion is going to be individual, but there's going to be 2 of them. And then I'm also going to have a sulfate ion, again, being entertained by water and floating around. Okay? So when we see this, an ionic compound dissolving in water, we have to make sure we recognize that the ions are now by themselves, surrounded with water molecules, dissociated from each other. Okay? And in an equation like this, we have to make sure that the number of the ions, in this case we needed 2 sodiums, is balanced with our coefficients.
Okay,
And
so that's already a balanced.
that's right. This one is balanced because we have a 2 in front of this sodium here. We needed 2 sodiums for 1 unit of sodium.
Okay, so
sulfate.
that's already a balanced.
Now, like I said previously, sometimes you won't see aqueous. People get kind of in a rush or lazy, or just know that everybody knows that when there is an ion in an equation like this, it's going to be dissolved and surrounded by water molecules, right? So sometimes you'll see the aqueous symbol kind of left out. All right, now we want to see if we can identify the ions and write how many ions there are, or that will result when these compounds are placed into water. Okay? So we compound. Do you want to try to name that compound? Any ideas for that one? That's names. And
Sodium phosphate.
yeah, sodium phosphate. Very good. Now I take sodium phosphate and it's in water.
That's
so can I
phosphate?
somehow identify what it's going to dissociate into? So I have, yeah, any ideas?
So would dissociate into 3 Na.
3 sodiums with a positive charge. Very important to remember that, right?
So
And
would dissociate into 3 Na.
Phosphate or the
Phosphate, PO4.
4 with a negative charge.
Negative what?
And then the phosphate
3.
or the
Negative 3.
yeah, 4.
That
4
is
with a
right.
negative
And
charge.
it's good. Yeah, it's good to look at the
Negative,
periodic table or the table
3,
of polyatomic
well,
ions,
let's
but you
wait.
can also see
Is
that
that right?
3 of
Oh,
these
that is
positively
right,
charged
'cause we got 3
sodiums
of those.
had to be balanced. Therefore, it must have been a 3 minus, right? Okay, good. So, how many ions in all result? 2 different kinds of
Right.
ions, right? But how many in all? If I put one of these in solution,
So we have 3 of the Na, right?
Right.
That's three ions.
So
And
we,
We have that throws me off.
3 of
It's
the
just-
Na,
it's just
right?
one.
So that's
just
3,
one PO4.
3 ions.
Yep, and there's
And
no
then
number
we
there,
have
but the coefficient is 1 when
now
there's
that
no
one
number.
kind of throws me off.
Okay.
We have
Very good. So
just 1.
we didn't write in the aqueous signs, but so I will write that in there like that. Okay.
Okay.
Great. Next one. Can you name that compound for us?
Aluminum sulfate.
Very good. Aluminum sulfate. Aluminum sulfate.
Okay.
Yep. What are the ions?
Aluminum.
So 2 aluminum.
Very
sulfate
good. 2 aluminum.
And okay.
Whoops.
And our charge on aluminum is
So 2 aluminum.
It's element number 13.
And our charge on aluminum is I gotta find it.
Yeah, so what does aluminum
okay.
do?
And
So it has 13 electrons, right? And it wants to have, what's the nearest noble gas?
well,
And-
the one would be argon.
Well, that's 1, 2, 3, 4.
Oh, I'm sorry. No, it's
right.
It's I can't read it, but I see it. Ne.
Neon, right.
Well, the nearest
So
one would
it's,
be argon. Oh no, I'm sorry. No, it's I can't read it, but I see it Ne.
It has,
Be a negative one charge.
And so
well,
it's
it has 13 electrons.
13, negative 3.
it's gonna
Or
be,
not negative, right? Because it's losing those 3 electrons
well.
to become 10 electrons,
that
right?
would be a -1 charge, right?
So positive.
Positive
Oh, 13
3.
-3.
That's right, positive 3. Very good. 2 positive 3, 2 aluminum plus 3 ions.
Oh, so, right.
Then
so
what else?
positive.
What is the other kind of ion?
Now,
And then our
okay.
Sulfate?
sulfate.
Okay, and then our
Which number is that?
It's on the back of the periodic table,
yeah,
right?
sulfate.
Oh, that's the.
Well, let me
Polyatomic
look back
ion.
here. Which number's that? Oh, that's the. Yeah,
There it is.
that's right.
It's a -2. -2. So -2.
Just a second here. So
So how many of those do we have?
so 4,
So
and there it is. Sulfate. Okay. Okay.
Sulfate.
Really?
I'm sorry. I saw the. That's right. We have.
So we have
there on the left side.
just
Yeah.
one of the
So
sulfate.
3 sulfates.
No.
Very good.
That's.
Now,
I'm sorry. I saw the.
There's another
That's
way
right.
that we
have
could have,
3 down
without
there
the
on the
periodic
left
table,
side, right?
remembered the charges, right? Remember how we can also do the reverse thing with the crisscross there, right? Remember that? So aluminum with the +3 there and a sulfate with the -2.
Okay.
Okay, very good. Let's go to the next one. What's the name of that next
yes.
compound?
Calcium chloride.
Yeah, calcium chloride. What are our resulting ions when it dissolves in water?
Calcium chloride.
Calcium is element 20.
Just
Oh, okay. So it's a
okay.
positive one.
+1. Where's calcium at?
Yeah, these always.
So it's
Okay.
going to.
So it's
Element 20, right?
Oh, yeah.
it's a positive one.
The noble gases are over. I'm sorry.
So it's
+2. Very good.
it's going to
And then our chloride ion, or what?
yeah. So it's going to the noble gases are over. I'm sorry, +2.
-1, right? Because it's element 17 and it has to go to 18.
And the chloride would be
Well, it does.
-2.
It does. And so,
So we got 2 of those.
yeah, that's right.
Oh,
2 of those
negative.
chloride ions.
That's right, -1.
Okay. Very good. I'll throw in a
So-
little aqueous symbol here.
I thought we'd have to be balanced for some reason,
Excellent.
right? So,
Okay.
all right, so we got
Last
2 of
one
those,
here.
don't we?
Can you tell me the name of that crazy thing?
Okay.
Calcium. Yeah, I gotta look on the sheet here.
Mm-hmm.
I get it's on the back.
Yeah.
Okay, so that's
calcium. And I gotta look on the sheet here. I guess it's on the back.
There it is. Permanganate.
Okay.
Permanganate.
Mn.
Okay.
Okay, so that's
So
yeah. Let me.
calcium
I just saw
permanganate.
it up there.
So what are our
Oh man, how
ions?
do you say that?
Okay, we're going to
Okay.
calcium,
One calcium.
and then we have
Okay, we're going to
now we have
one calcium,
two of those of the
and then we have
Permanganate's good. What are the charges on them?
plus. Yeah, now we have
the calcium
two of those of the manganese.
Positive. We always have to say the number that the positive
We're going to
is.
have two of those,
Okay,
and we have on the calcium
Element
we have a
20.
positive charge.
that memorized already, but
You will. Gradually, we're using it over and over. We'll get it.
Okay.
Element 20.
positive 2 charge.
Positive 2. Very good. And then the permanganate,
You know, I should
MnO4.
have that memorized already, but I.
Negative charge.
Negative, and we always have to say the number.
Okay, so it's a positive 2 charge.
Or look, could we use the crisscross?
Yeah, we can.
What's the
So,
Yeah, that had a negative charge. Well, let me look on this.
would be
Yeah, let me.
minus 2 charge.
well? How many permanganates
Yeah, we
do we
can.
need for every calcium?
So,
This charge, and we have
well, I know we can. I just.
2 of those.
It would be a. Well, I want to say minus 2 charge, but.
In total, it's a minus 2 charge.
That's
It's a
right.
mi-
Two of them
it's a
provide a
minus
minus 2 charge, so each
charge,
one must
and
be a
we
minus
have
what?
2 of those.
Yeah, minus 1. Minus 1. Very good.
So that's what we're okay. So we write it.
Yep.
In total, it's a
Aqueous.
minus 2 charge.
Okay.
And that's what we found on the back. It says just a minus charge.
Yeah.
Just a minus charge, a minus 1 charge.
Okay. Very good. Now,
So that's what we're okay. So we write it like
how about
that.
this?
Okay.
Let's see if you can remember some information we talked about before.
And that's what we found on the
Which
back.
of
It
the
says just a
following
minus charge.
would not be expected to
Right.
produce
If you
the
just-
chloride ion when it's dissolved? When it dissolves.
So look at P is what is that?
Phosphorus, it's element 15.
Okay.
Okay.
And so and Li is
Lithium, element 3.
So let me look at P is what is that?
so then it would be
Okay.
phosphorus.
That's right. That's right.
And
Why?
so
Why won't phosphorus
and
produce
Li
chloride ion?
is
Well, I just eliminated that.
oh okay. So then it would be
Let me see if I can figure it out.
phosphorus.
Well, it's
Well, I just eliminated that.
That's
too,
right.
But,
It's a molecular compound, right? And the molecular compounds
let me
don't
see if I can figure
ionize
this
when
out.
they're placed in water. Right?
Well, it's
Hey. Good job.
it's a non-metal.
So, how about this one? How many ions form upon the dissociation of sodium phosphate? How many ions do we end up getting?
Right, right.
Now, it's not asking how many different kinds of ions, right?
okay. Distinction one more time.
It's not asking how many different kinds of ions. We see that there's sodium ions and phosphates ions, so there's 2 different kinds. But we want to add up all the different ions that,
Okay,
yeah,
so
result.
we
How many
have-
will result?
Okay, make that distinction one more time.
3 then.
Any?
4.
That's right. That's right. 4.
Phosphate, right.
3 phosphates, right?
Now, we're
Sorry.
looking at how many,
3
right?
sodiums
3 sodiums and 1 phosphate.
and 1 phosphate. Very good.
So
How about for aluminum
3 then.
sulfate? How
I
many
mean 4.
ions will form
Sorry, 4.
upon the dissociation of aluminum sulfate?
Well, 3 sodiums and 1
5.
phosphate.
Very good. 5 for aluminum sulfate. Excellent. So now when we write chemical equations, like this one here,
So 5.
this is Ag. Do you remember what Ag is? What metal Ag is?
Yeah, that's silver.
Silver. Very good. How about NO3? You want to look on the periodic back of the periodic table and see what that one is?
Yeah, that's silver. Okay.
Oh, there it is. It's nitrate.
Nitrate. Very good. So we got silver nitrate, and that second one, what's that one called?
Why can't I find this?
K is potassium.
Potassium chloride.
Oh, there
Potassium
it is.
chloride. Silver nitrate reacts with
It's,
potassium chloride
nitrate.
to form, what's that one?
Silver chloride.
Silver chloride, good, and
potassium.
the
Potassium
NO3 was
chloride.
the nitrate. The NO3 was the nitrate, right? All right.
So that's I'm sorry. What
Silver,
was K?
silver
Potassium.
chloride, solid,
Potassium nitrate.
Yeah.
and potassium
So when we see this chemical reaction,
nitroxide.
and we see these ionic compounds
Okay.
that are aqueous, silver nitrate,
So
it's aqueous.
That's
see?
I'm sorry. What was
Potassium
K
chloride,
again?
it's aqueous. Silver chloride is solid,
Potassium
but potassium nitrate is also aqueous.
Right. Okay.
So when we see that these chemicals are aqueous,
Okay.
these ionic compounds are aqueous, then we can rewrite this equation in what's called an ionic equation, where everything that's aqueous, every ionic compound that's aqueous, is separated into the appropriate number of ions. So silver nitrate was aqueous, therefore it separates into silver ions and nitrate ions. Potassium chloride was aqueous, so it separates into potassium ions and chloride ions. Silver chloride is a solid, so we keep it the same. You see that? But the potassium nitrate breaks up into its ions as well. So just like we were doing on the previous slide a couple bits ago, a couple slides back, we take the ionic compounds and we separate them into their ions in what we call the ionic equation. The ionic
Okay.
equation.
Can we pause for a second?
So if we look at this ionic equation up close, we see that we're taking silver ions and nitrate ions. Let me scoot back a little bit. Silver ions and nitrate ions, combining with potassium ions and chloride ions. And because when silver ions interact with chloride ions, they form a compound that is insoluble. And we can see that on our periodic table, the back of our periodic table, our solubility rules. Chlorides are generally soluble, but it has some exceptions, and silver is one of them. So if the silver and chloride ion find each other, they form a solid, silver chloride. And potassium ions and nitrate ions, they will not form a solid, so they still stay in their ionic form. And so in this reaction, we have the ability to kind of simplify the reaction and express it in what we call a net ionic reaction. Because in this ionic equation that we've drawn, some stuff doesn't change from the left side of the arrow and to the right side of the arrow. So for example, the potassium ion, it doesn't do anything. It's potassium ion on the left and it's potassium ion on the right. And so we can get rid of the potassium ion. Same thing with the nitrate ion. It's the nitrate ion on the left and it's the nitrate ion on the right. It's exactly the same thing. And so we call those spectator ions. They were there because they came with their counter ions, but they didn't do any chemistry. And so we crossed them out for the net ionic equation. and the resulting net ionic equation is just where the business occurs. The silver ion finding the chloride ion to make silver chloride. They were ionic, aqueous, and now they are solid. Okay, so we have our chemical reaction, sometimes called the molecular equation, which is, kind of a dumb word in my mind because nothing's molecular about this. This is all ionic compounds. But we have our initial equation, and then we have our ionic equation, where we've separated our ionic compounds into their ions, and then we have a net ionic equation, where the business is left because we've gotten rid of the spectator ions. Okay? So, writing our ionic equations, we essentially look at the initial equation. If something is written an ionic compound with an aqueous sign, we split it up into its ions. And then after we get the ionic equation, we get rid of our spectator ions to find out what's the net ionic equation. So here's an example of another chemical reaction where two ionic compounds, in this one here we have lead nitrate and potassium iodide. We mix lead nitrate, aqueous obviously. Lead nitrate is a solid usually, but it's here dissolved in water. Potassium, again, a solid, but here it's dissolved in water. Mix these together, and the lead ion finds the iodide ion and forms lead iodide. And that's this orange color that you see here. It becomes a solid. It becomes a solid, right? So here we have the lead ions and the nitrate ions, the potassium ions and the iodide ions. They don't form solids individually, but when the lead is introduced to the iodide, it forms a precipitate or a solid. So we take two aqueous solutions, mix them together, and we result in a solid. That's called a precipitation reaction. And this is your first kind of chemical reaction, a precipitate reaction. Here's a video of another one. This is silver iodide and mercury nitrate. And essentially, what's occurring here is the same thing. Two aqueous solutions, solids dissolved in liquid into water. But when we mix them, we get a powder, a solid. All right? It's not a big, huge chunk of something. It's just a solid material that now is floating throughout, kind of like putting flour into water. The flour won't dissolve. It just kind of spreads around. Okay. So here's some chemical equations where we combine barium chloride with lead nitrate, and the products are, and you can see how the products are the ions trading partners. You can see how barium here in the products goes with the nitrate, whereas the lead goes with the chloride. Can you see that? And it follows this general pattern that we have where we see, say, compound AB combines with compound, and again, this is aqueous, is mixed with compound CD, aqueous, and the result is A, the cation on the left, going with the anion on the right, D, and C, the cation here, going with the anion there, B. And then one of these is generally going to be solid, and the other is going to remain aqueous. Some scenarios, they're both solid, right? But we have a general formula of AB plus CD forming AD plus CB. Okay? So that is how our first chemical reaction, which we call a double replacement reaction, all right? A metathesis reaction, also another name for it, and we'll talk about those names later. But we can look at these chemical reactions here and write the ionic equation for each of these. All right. Now, to write the ionic equation, we need to look at the compounds and identify what ions they should be broken up into. So if we start with barium chloride, BaCl, right? BaCl2, sorry, barium chloride there. What is it going to break up into in the ionic equation, when we rewrite the ionic equation? What are our ions?
So one.
One is barium.
So one
Barium is
BA.
element 56. It's in the second column, so it has a +2 charge. All right. Whoops, 2.
Okay.
And what's the other ion?
Then we'll have.
That's right.
We're going to LB2.
Number 17.
17. Yeah. And that's
Minus-
going to have a
A
minus.
Yeah,
well,
minus
no,
1.
no,
Right.
I mean, it'll be a minus
So
1. Yeah.
barium, chloride ions. Next, how do we write this compound? Lead nitrate. It's aqueous there, so we break it up as well. What do we got?
Okay. So we'll have one.
Lead, like plumber. Right,
What's
plumbic,
PB
yeah.
again? Oh, lead. Okay. And so, yeah, just one of those, but now we have.
We need a charge on that, right?
Well, we don't need it yet if you.
Oh,
if
and we need a
it's not
charge on
coming
that,
to
right?
mind.
Right. We can't figure. Okay, so.
Oh, yeah, that's right. 'Cause we can't figure. Okay, so, and we're going to have 2.
Yep. Those are nitrate ions. So you
NO3.
can look on your polyatomic ion chart and find out what the charge is on there.
Okay.
And we see that it's a minus charge.
Yeah.
And
minus
we
1.
see that it's a minus
So what does that mean the
charge.
charge is on the lead ion?
So the lead ion would be a positive.
So
Positive.
the
Now,
lead
whenever
ion
we say
would be a
positive or negative, we
positive
always
charge.
have to have a number with it.
Okay, yeah, I'm sorry, a positive 1 charge.
Positive 1 charge
Okay, yeah, I'm sorry, a positive 1 charge.
on the lead. So why is there
On the
2
lead,
of these
right?
negative charges then?
Um,
I guess, yeah, it would be a positive 2 charge.
Has to be a positive 2. Very
I
good.
guess, yeah,
Very
it
good.
would be a positive 2 charge, huh?
All right. The other side of the equation, lead chloride, PbCl2, it's a solid. So that's nice. We don't have to write that as as ions. Okay. But the rest, barium nitrate, what are we going to write?
Right. Okay, so
1 barium. Good. What's the charge on the barium?
1 barium,
And that's going to be a plus.
and that's going to be a plus.
I just want to plus something. I got to look up on that.
Element
I just want to plus something.
56.
I got to look on the.
Okay, so plus 2.
Very good. And
Okay, so plus 2.
what's in the end there?
Now we have
And then we have
somehow I lost my place there. Okay, NO3, right?
somehow
Uh-huh.
lost
That's right.
my
Okay, so we
place there. Okay, NO3, right? Is what's okay. So we, I mean, NO. So
2
we
of
we'll,
the NO3s. And what's
sorry,
the charge on the
we'll
NO3?
have 2 of those.
and it would have to be a
And
That's right. -1.
it would have to be
Very
a
good.
-1.
So that there is what we call the ionic equation for that chemical reaction. Excellent. We'll save that second one there for next time. We'll pick back up and it'll be a good review for us as well. Okay, good job today.